Hi everyone. So is there any question about the course, the previous lecture, or the assignment? So we have posted the assignment 2. Yeah, about the project, the assignment, everything is clear. By the way, the deadline of the assignment was mistakenly written as February 25th. It's March 25th. I corrected that. It was a typo. I think. Shall I start? Can you give me some feedback? Okay, I start. Great. Let me share the screen. Okay, so and we in the last session we talked about first order methods, stochastic gradient descent, and it was also backpropagation. But now one other category of first order methods is left, which are the proximal methods. And so what are the proximal methods? Definition. Proximal mapping or operator, it's also called either proximal mapping or proximal operator. What is that? Assume that function g is a convex function. So we write it in this way. So prox subscript g x is defined as this: argmin of this term gu plus 1 over 2 squared L2 norm of u minus x. And what does it mean? So assume we want to minimize a function g x with respect to x. So something like that. When we have this, we are having a change of variable. We are saying that minimize g of u with respect to u, but we add the subject where x should be equal to u. So this is a good technique in optimization. We can have a change of variable, but in this constraint of the optimization, we say that that variable, the variable x, which was the original variable, should equal to y. In other words, rather than this, we can say this should be minimized. Minimize the distance between u and x, right? And because we know that the derivative of the squared L2 norm will be 2 u minus x. In order to cancel these two, we can have 1 over 2 behind that in order to cancel that too. So what we are doing, we are having this optimization problem. We are having a change of variable where we are saying that in the constraint set x equal to u, and then we have a third step. We are saying that let's convert this constraint optimization problem to an unconstrained optimization problem by adding the constraint as a regularized term. We are penalizing the constraint. Okay, so 3 steps we are having. Minimize g with respect to x. Now let's have a change of variable, but in the constraint we say that x should be equal to u. And then in order to make this unconstrained again, we are putting the constraint as a soft penalty. So because this is a hard penalty, right? We are having a soft penalty as a regularization term in the objective function. This is the same idea that we had in the Lagrangian function. You remember in the interpretation of Lagrangian, we said you can interpret it as a regularized cost function. It's a good technique. Whenever you have a constraint, in order to make it unconstrained, you can softly penalize the constraint. So now this is what exactly the proximal operator is doing. See, it's the variable is x, but we are having a change of variable to u. Then we say g of u rather than g of x, and this term is penalizing. It's the distance between u and x. So x becomes equal to u, something like that. And note that this is not the function value, but the argument which minimizes that argument. So the u which minimizes this term is equal to the prox of x with the function g, right? So this is a definition of proximal operator. I think now you understand what it is doing. It's saying that minimize the function g with respect to u, but try to set x and u close to each other. Okay. So in case the function g is scaled, we might also have, do you remember in the regularized term, which is a soft penalty, we can have a regularization term to weight between the actual cost function and the regularization term. We can put the regularization term lambda in the numerator or in the denominator, doesn't matter. As long as it's a parameter, that's enough. So let's put it in the denominator, and then it becomes here. So the parameter lambda, we put it here. So in a general case, the proximal operator is this with the parameter lambda. And when we set lambda to 1, we'll have this. Okay, there is a question in the chat. Okay, someone said hi. Hi, Milad. So we have this proximal operator generally with a parameter lambda, but when we set lambda to 1, we'll have this. So far clear? Any question? No? And by the way, this argmin returns the u star, which minimizes that, and as we set u to be very close to x, therefore this makes sense because prox is a function of x, but we are setting u to it, but u is very close to x, therefore it makes sense. Makes sense to equate the left-hand side to the right-hand side. Okay, now we'll see that this proximal operator has a lot of use cases in optimization. We'll see how. A lot. It's a family of methods, actually. So what is proximal mapping? We talked about it in the previous slide. Now we know that we are going to say that it's very closely related to the Moreau-Yosida regularization, which we define below. So Moreau-Yosida regularization, also called Moreau envelope. You can look it up in papers 27, 28 in the references. So this the Moreau-Yosida regularization or Moreau envelope of the function g is defined as this. As you see, it's very related to the proximal mapping. Compare these two. So the difference is that here we have arc. Here Moreau envelope doesn't have arc. It's a function value, an optimal function value, and inf is minimum, a generalized case of minimum. Do you remember? Recall the preliminaries. And except that, everything is the same. By the way, when we have lambda here, we have lambda here. So we might have lambda here. Very similarly related. And there is, according to reference 29, the Moreau-Yosida regularized function has the same minimizer as the function g. So the minimizer u star, which minimizes g, also minimizes this envelope, this Moreau envelope of the function. That's an interesting fact. Okay. Now Moreau decomposition, we also have Moreau decomposition proposing reference 30, is that we always have the following decompositions. These are called the Moreau decompositions, these two. So this is this when we set lambda to 1. So you can write x as the prox of x with function g plus prox of x with function g star. And what is g and what is g star? G is a function in some space. G star is the corresponding function in the dual space. We already talked about dual space in the preliminaries. You remember we had norm, dual norm, for example. So if G is a norm, G star is the dual norm. Or if G is projection onto a cone, G star is the projection onto the dual cone. We'll talk about projection in a few slides. Wait for it. But if G is projection onto a cone, G star is projection onto the dual cone. Again, we talked about dual cone in the preliminaries. These are some examples. In the parentheses, I'm saying that. So G and G star, G is a function, G star is a dual function. And writing x as the prox of x in G with function G plus prox of x with function G star is called Moreau decomposition. The left-hand side x equals the right-hand side, the summation of these two terms. And the more general case with parameter lambda, we have this. Okay. That's an interesting thing. We can write any variable x as the summation of two terms, prox of g, prox of x with function g, and plus prox of x with function g star. Okay. If you have any question, please feel free to interrupt me. Okay. But walk with me through these algorithms, and you will see the beauty of them. Okay. In optimization, indicator function, what is indicator function? So indicator function in optimization, it says that for it is defined for a set. Assume S is a set, and indicator function of whether X belongs to the set S or not. If it is defined as this, we write it with I, X, whether it is in the set S or not. I stands for indicator, okay? If X belongs to S, this indicator function is 0. If it doesn't belong to S, this indicator function is infinity. You might, especially if you have worked in machine learning, you might be wondering, we have another definition of indicator function. There is another one which usually many people use, that says that if X belongs to S, it's 1, so it's a binary function. If X doesn't belong to S, it's 0. However, here in optimization, we usually use this definition. So we say when it belongs to S, it's 0. And when it doesn't belong to S, it's infinite. Do you know why? Can someone tell me, why do you think we have such thing in optimization rather than this one? Can you please give me your guesses?
Is it so the output is always either 0 or infinite, where if it's in the denominator, then it'll either be 0 if it's not S and infinite if it is S, and vice versa in the numerator?
But do we have a fraction here? That's a good answer, but it might be working if we have a fraction, right? We don't necessarily have a fraction here. My question is, why does it make sense to have such indicator function in optimization? Why does it make sense to say to have it blow up when it's not in the set S, and becomes 0 when it is in the set S? Why don't we say whenever it's in the set S, let it be 1, and if it's not in the set S, let it be 0? Can you have other guesses? So it makes sense. The reason is this. It makes sense because we want to use this for penalty. This is a hint. Now, can't anyone tell me why it's useful for to have this definition of indicator function in the as a penalty, as a regularization term, for example? Guys, are you with me?
Sorry, I just joined, so I'm trying to catch on, but I'll add my 2 cents. I guess if it's a penalty,
Okay.
then you want to add to it, right? Like you want to, if it's not within the set, so you'd have like a value of 1, then you're adding a penalty. If it's 0, then you're not adding anything.
Exactly, but you said why did you change infinity to 1? So your explanation was correct, except one thing. You said when it's not in the set, let it be 1. No, let it be infinite. Why? Why do we want it to blow up? Exactly as you said. When it's not in the set, we want the penalty to be infinite. Do you get it? So in other words, assume the indicator function was this: 0 and 10, or 1, 10, whatever. This also makes sense. But what is the difference between these two? Can you tell me what is the difference between these two? So
Well, is infinity not just a larger penalty?
Yes, exactly. But why do we want the penalty to be infinity? So here, so whenever it's not in the set S, we are penalizing it, but with value 10. When here, it's not in the set S, we are penalizing it with value infinity.
Well, the speed of training, would the speed of training not be altered? So if you use 10,
okay,
you would have to potentially train longer.
yes, you are discussing on the pacing of the algorithm. That's a good analysis. That's correct. With another perspective, you can say, if it's 10, we have a soft penalty. If it's infinite, we have a hard penalty. Do you see the difference? The difference is that assume belonging to S with I'm changing this example to another example. So belonging to S, assume that is like, let's have a harsh example. So by a harsh example, you will understand what I mean. I say, okay, for example, if belonging to S means for me, let me think. Assume I want to say an example which is not controversial. Let me think. I don't know, but don't take it personally or controversial. I just wanted for the concept to be understood. Assume I'm saying that if I belong to the set scientists, then I'm done. If I don't belong to the set scientists, I will penalize myself in a way that in the first case scenario, in this case, if I don't belong to the set of scientists, I will penalize myself. For example, I don't eat myself food. I don't eat myself pizza. I will tolerate hunger or something like that. In this case, it says that if I don't become a scientist, I will kill myself. You'll see. This is the difference between soft penalty and hard penalty, okay? So in this case, we are penalizing with some point, but what is the most harsh penalty or hard penalty in this example that I said is killing, right? Because we don't have worse than killing. So in optimization, we are saying that whether in this case, we are saying that try to belong to the set S, otherwise I will penalize you. In this case, I will say, if you don't belong to the set S, I will kill you. Why? Because when you are minimizing a function f or something, when function f becomes infinite, because we are summing this regularization term in the function f, right? In the objective function. We are saying that when you make this objective function infinite, it's exactly opposite of minimizing, right? Or if you are maximizing it, then this should be minus infinity. So whenever you have infinite in optimization, it's equivalent to killing. It's the worst case. Is it clear now? Can you tell me?
Yeah, essentially it's making like a discrete difference.
Exactly. The difference is between soft penalty and hard penalty. Again, we had this concept of penalizing penalty previously. So consider the case of Lagrangian and the optimization problem that we had. The optimization problem, when we had the constraint was a hard penalty. But when we had a regularization term, in any case, such as Lagrangian, we weighted that with some lambda or something like that. And we said, okay, let it be a soft penalty. So the constraint was hard penalty, let it be a soft penalty. However, when you're adding that penalty to the objective function, you can also make it a hard penalty by saying that if it's not satisfied, let it be infinite. So we can have two kinds of hard penalty. Either let it be a constraint when it's not satisfied, the solution is infeasible and it's not acceptable. So it's also a hard penalty when it's in the constraint. But when you add it as a regularization term to the cost function, then it's a soft penalty, but you can convert this soft penalty to hard penalty by saying that let it be infinite, let it be the worst case for optimization when it's not satisfied. Is it clear? In other words, minimize f of x subject to g of x, for example, less than 0, this is a hard penalty. This is a hard constraint, right? One thing we could, in order to convert it to an unconstrained problem, we could say, okay, let it be lambda g of x subject to, I think it's better for me to write it in another page. Give me a second. This is an important concept, not related just to this part. It's related to all optimization algorithms that I'm talking about. Let me think. Oh no. Where am I? Okay. I think I jumped to another page. Give me a second. Let me print. Sorry about that. When you understand this, you will understand a lot more about optimization. That's why I'm focusing on this concept. Yeah, I think it's better for me to add a page here. Yeah. Okay. Okay. So soon we have a constraint optimization problem. We can, in order, a good technique in order not to make it unconstrained, because unconstrained solving unconstrained optimization is much easier, is adding this constraint as a regularization term. So when G becomes, for example, in this case, when G becomes large, because G should be less than 0, so it should be small. So when G is large, then it should be penalized. This is the same idea that Lagrangian had. So this is a penalizing regularization term. This is regularization parameter lambda, and this is regularization term. So we are penalizing. This is a penalty term or regularization term. But this is a soft penalty. This is a hard penalty. Because why is it a hard penalty? Because if you don't satisfy that, it becomes infeasible solution and you don't accept it. So it's hard. Here, if it roughly satisfies G, or G is roughly small, you accept that. Maybe it might be, for example, G might be 0.001. It's not less than 0, but it's small enough. You accept that, but with a small penalty, you accept that. So it's a soft penalty, although you don't accept G equals 10, for example. 10 is much larger than 0, but because the penalty for that will be large. But when it gets close to 0, you accept that, you tolerate that, right? You tolerate that. However, we can convert this unconstrained problem, which is a soft penalty, to an unconstrained problem with hard penalty. How? We say that let the regularization term be a hard penalty. How? By this. Say the indicator function of x of g of x less than 0. So this is the set. The set is having g of x less than 0, less than or equal to 0. Now, the indicator function, when g of x is less than or equal to 0, indicator function, it becomes 0. That's why in optimization, we say when the set is satisfied, the constraint inside the indicator function is satisfied, that it be 0, because I don't want to penalize that. But when it's not satisfied, let it be infinite. So it blows up the whole objective function, and you don't accept it, because this is the worst case scenario for minimization. Now you can say, although it's unconstrained, it's a relaxation of this constraint problem, but it has a hard penalty. So a good thing, this is approximately correct. So approximately soft penalty approximates the hard penalty. The solution might not be exactly equivalent, but these two are exactly equivalent. Because when you don't satisfy here, it's infeasible. When you don't satisfy here, it blows up the objective function. So you must satisfy the constraint in these two cases. Therefore, these two are equivalent, although one of them is constrained and the other one is unconstrained. But another thing might happen, the fourth case scenario might happen. Sometimes you can't solve this in practice. In practice, not possible. Right? How do you code infinity in practice? In theory, it works, it makes sense. They usually approximate, let's now approximate, because you can't code indicator function in your code in machine. Let's approximate the indicator function itself. We will see that in this session. When you approximate that, you change the hard penalty to soft penalty again. But there is a but. What's the difference between these two soft penalties? Is that this is more accurate, because it's approximating the hard penalty of indicator function. Usually this soft penalty is more accurate than this soft penalty. In this soft, because this soft penalty blows up faster or more than this soft penalty. Now, did you get it? So in order to understand indicator function, consider it as killing, murdering in optimization. So when it's not satisfied, you are killing the optimization problem. That's why it becomes a hard penalty. Here, you're approximating killing with a very huge penalty. Any question? Did you understand the concept of relaxation, regularization, soft penalty, hard penalty? All of them were explained in this slide. Yes? Okay, great. Now let's go back. This was a parenthesis. Let's go back to this slide. So we were talking about the indicator function, which is an important thing. Now, we have a projection onto a set. The proximal mapping of an indicator function. So proximal mapping we introduced in previous slide. Indicator function we introduced in this slide. Let the set S, which we have here, let it be convex. So the indicator function says whether x belongs to the set S, and one example of set S was g of x less than or equal to 0. So set S can be considered as a set of feasibility, as a set of constraints, for example. It can be any set. So projection of the point onto the set S. So the proximal mapping of indicator function, the proximal mapping, let the function g in the proximal mapping be indicator function. We will prove in the next slide that the proximal mapping of the indicator function equals this, and this is projection onto the set. Why? I will tell you. So assume I'm explaining why this right-hand side is projection onto the set S. Assume this is the set S. This is the point X. Okay. What does the right-hand side of equation 63 say? It says that when you have a point X and you have a set S, this says find argument, find a U in the set S. So U must belong to the set S, one of these points. It can be on the boundary too, or it can be inside the S. So among these points inside the set S, including the boundary, find a point which is closest to the point X. Why? This means the minimize between the distance between U and X. And this is the L2 norm. We already talked about it, is the Euclidean distance. And this is a squared Euclidean distance. And this 1/2 is just for cancellation of derivative of a squared, right? So this is saying that minimize the Euclidean distance between U and X. So which point in this set S is closest to the point X? Of course, this point. What I said, the sentence I said is the definition of projection. The definition of projection is find a point U in the set S which is closest to X. This is the definition of projection. So that's why. And we denote projection of X onto the set S by this, for example. And here is the point U, the projection. And when you connect the point X to the projection of X onto the set S, that line will be perpendicular to the set S because it has the shortest distance, right? And now this equality, we didn't prove that. We are going to prove it in the next slide. Why is the proximal operator of the indicator function equals the projection of the point onto the set S? Let's see. It's because of this. So this was the lemma. We are going to prove this. We are going to prove this equation. This was the proximal mapping that we introduced, we defined a few slides ago. Now, so let's start with the proximal mapping of the indicator function, the left-hand side here. So according to the definition of proximal mapping here, we have this. So I'm replacing function g, because function g is indicator here, with indicator function of x belonging to the set S, right? And what is this? We can write this. So when this is 0 or infinite, 0 when if x belongs to S, otherwise it becomes infinite. So if it becomes infinite, it blows up the minimization. So we have to satisfy it. Therefore, rather than u, we can say that u must belong to S in order for this to be 0. Otherwise, it blows up. And when u belongs to S, this becomes 0. So it goes away. Then we will have only this term. And the right-hand side, we already talked about it in previous slide. That is the projection. And now you see that the beauty. So we talked about it. We said that it's also related to the hard penalty and soft penalty. So it's saying that you find the closest point to the x in the set S, which satisfies the set S, the feasibility set. Otherwise, it blows up the optimization. So this is a projection. So assume you find a solution to the optimization problem, which is here, but it blows up. It's infeasible point. Now, indicator function is saying that find the closest point in the feasibility set to the solution that you had. Project it onto the feasibility set. Any questions so far? No? Okay. So, Moreau decomposition, we just talked about it. With parameter lambda, this is the definition of Moreau decomposition. Now we can rearrange it to have this, right? Okay, now we are going to use this. If the function is a scaled norm, so assume that function g is lambda some norm. This norm can be any norm, like L2 norm, L1 norm, any norm. Then the prox just replace this with function g here, and you will have this. We'll see why. So give me a, what is this? This is according to what we had here. Look at this, which we proved here. Look at this. Proximal operator for the function indicator function is this. Okay, wait, give me a second. Give me a second to, yeah. So when we say that, because we set g to lambda, right? Then g star, what is g star? Is lambda norm star. Norm star means the dual norm. So now I'm replacing g star with lambda norm star. X over lambda. So this lambda and lambda cancel each other. So this becomes prox of x over lambda with the function lambda star, right? And I think, yes. And what does it mean? It means that project it here. According to what we just talked about, this is an indicator function whether the input is in the dual norm or not. Therefore, it's a projection onto the dual norm. What projection onto the dual norm on the norm or dual norm means that you project onto its unit ball. Do you remember unit ball that we talked about in the preliminaries? So when you project onto a norm, it means that you're projecting onto its unit ball. So B is a unit ball of the dual norm because of the same reason that I just talked about it here. So I'm projecting I'm saying that whether x over lambda here belongs to the set of the dual norm or not. Now I'm going to use equation 64, which is the proximal operator for the norm. So when the function g is a norm or the scaled norm, its proximal operator is equals to the x minus lambda projection of x over lambda onto its dual norm, onto the unit ball of its dual norm. Now we are going to use that. Why is it useful? We will see. We'll see in a few slides. It's a useful equation. Now let's find the proximal operator for several of the norms. First off, let's talk about it. If the g is a zero function, what happens? Proximal operator. What was the proximal operator? Do you remember the proximal operator? The definition of proximal operator. Yeah, or proximal mapping. This was a proximal operator, right? I'm gonna use that, but I'm putting g to 0, setting g to 0. Let's see what happens. So I'm setting g to 0. This is the definition of proximal mapping, but I'm setting g to 0. So 0 goes away, and we'll have this. And what is this, by the way? Find u where the distance of u and x is minimized. This is a non-negative term because lambda is non-negative, and this is a squared L2 norm. So it's either 0 or positive. Its minimum is 0, right? When does it happen? It becomes 0 when u minus x squared is 0. So when u equals x. Therefore, the solution is x because it's the argmin, right? You might be wondering, it's very similar to what we had in projection. However, there is a huge difference. Don't confuse that. In projection, we had argmin of this, but u was in the set S. That's why it was projection. It didn't become x because x might not be in the set S. It might be outside of the S. So it's projection of x onto the set S. Here, u doesn't have any constraint. Therefore, u can become x. So when g is 0, the proximal operator is an identity function. Its output equals its input. Now, let's talk about the proximal mapping of L2 norm. Proximal mapping of L2 norm. By the way, you can see a lot of proximal mappings of many different functions, such as norms and these things in reference 31, chapter 6. But we are saying some of them. So proximal mapping of L2 norm is this, and we'll prove that. So if the function g is the L2 norm, then its proximal mapping is 1 minus lambda. Lambda is the parameter here, parameter of the proximal mapping. Lambda over max of L2 norm of x and lambda times x. What is this? It means that when the L2 norm of x is greater than or equal to lambda, then the denominator here becomes L2 norm of x. So we'll have 1 minus lambda over L2 norm of x times x. If this L2 norm is less than lambda, this max becomes lambda, the denominator becomes lambda, then lambda over lambda is 1, 1 minus 1 becomes 0, so this becomes 0. Now let's prove this equality. Why is it the case? So do you remember in the previous slide we just showed that the proximal mapping of a scaled norm equals this over norm. Now let G be the L2 norm because we are going to prove for L2 norm here. So its dual norm, do you remember this? This is projection. This is projection onto the unit ball of its dual norm. What is the dual norm of L2 norm? We already talked about it in the preliminaries. It's a dual L2 norm again. The dual norm of L2 norm is dual L2 norm. So this is projection onto the L2 norm. And what is projection onto the L2 norm? Let's draw the L2 norm. Do you remember L2 norm? Unit ball of L2 norm. In 2 dimensions is this. In 3 dimensions, it's a sphere containing itself. It's a ball. So this is L2 norm. Also, it includes itself inside of it because it's ball. And when we have a point, for example, this X, when it's outside this sphere, this circle, its radius, because its radius is 1, right? Then you need to project it onto this unit ball. And what is this projection? It's because you consider this vector. When you project it, it becomes here, right? Let me draw it again. So this is the point. This was the vector, but now you are projecting it, so it becomes here. So it becomes here. This was X, but what is here? It's X over the L2 norm of X. In other words, the length of X becomes 1. What is the length of this? It is 1. Why? Because you can write it in this way. This is a constant, so it comes out of the norm. So this is 1. Projection of the point X onto the unit ball of the sphere, it means that you just set its length to 1. You normalize it. You normalize its length. So that's exactly here. But when you are inside the ball, you are already in the set. So you shouldn't do anything to it. This is a projection. I visualized it here. Okay, now let's use it. Let's use it. So I'm using it here. I'm saying that X minus lambda this, and what is this? We just talked about it. So when X is, so here, when inside of it was greater than or equal to 1, therefore it means that when X over lambda is greater than or equal to 1, in other words, when X is greater than equal to lambda, then we have this 1 minus lambda over this xy. Let me write it in this way so you understand better. Bear with me and you will see the beauty of these algorithms. You need to be patient for why these are important. So when we have this, so inside the projection is greater than or equal to 0. In other words, when X is greater than or equal to lambda, we'll have X minus lambda, and this term becomes normalized. So 1 over lambda, X normalized. These two lambdas cancel each other, right? Am I right or wrong? Give me a second. Give me a second. I'm not sure about this, but this might, I need to think about this lambda here, and I will talk about it in the next session. There is no time for me to dig into it, but I think there might be a mistake here, but doesn't matter. I think you get my point. You will have this, but when X is less than lambda, what does it happen? You will have this. Look at here. You will have X minus lambda is this itself. So these two lambdas cancel each other. X minus X is 0. Now we prove this. Again, I'm a bit doubtful about this lambda, but I will look at it with more detail and I will talk about it in the next session. But I think you got the general idea. This is the proximal mapping of the L2 norm. Now let's see the proximal mapping of L1 norm. L1 norm as it is, do you remember L1 norm is a non-smooth function. Therefore, we have to work on it component-wise or element-wise. It's not as easy as L2 norm. But let's see. So when you have a vector x, a d-dimensional vector x, let xj denote the jth element of that. Okay. And by the way, the proximal mapping of x with function lambda L1 norm. Do you remember it was returning argmin, which was the u, okay? And u has the same dimension as x. When x is d-dimensional, therefore proximal mapping is also d-dimensional. And we can denote its jth element by this, proximal with jth. I denote it here in this way. Okay, now the jth element of the proximal mapping of the L1 norm is this. We will prove it. Is maximum of 0 and this term. So this is the absolute value of the jth element of x minus lambda. If it's greater than or equal to 0, then this maximum becomes itself, this x itself. If it's less than 0, then this maximum becomes 0. Okay, then we have times sine of xj. So if xj is greater than or equal to 0, it becomes 1, the sign becomes 1. Otherwise, if it's negative, the sign is negative 1, minus 1. And we denote this function by s of lambda xj, and it is this. Why? Let's talk about the equality of this term and this term. Let's see. So when xj, the jth element of x, is greater than or equal to lambda, this becomes xj minus lambda. And as xj is greater than or equal to lambda, the whole max becomes xj minus lambda. And sine of xj is also plus 1. Why? Because lambda is already a non-negative number. Therefore, we'll have xj minus lambda. If the other side, if xj is less than or equal to minus lambda, then this becomes minus xj minus lambda, and we know that give me a second. Yes, this becomes minus xj minus lambda, the whole max, and the sign of xj is also minus 1. Therefore, we'll have xj plus lambda. Now let's see the middle case. When the absolute value of xj is less than lambda, so if xj is between minus lambda and lambda, this maximum becomes 0, and the whole thing becomes 0. I have plotted this function here. You will see that, why is it here? Because when we have this case, we are in this region, and the function becomes 0. When xj is greater than lambda, then we have this line with a slope 1. When your xj is less than minus lambda, we have this line with slope 1. This function is called soft thresholding function. We denote it by here, s lambda xj. So the parameter is lambda. These are the parameters, right? And the input is a scalar. Note that we are talking about it element-wise. So although it's a vector, x is a vector, but we are talking about each of its elements for j from 1 to d, right? Okay, now let's prove this equality. Why is the proximal mapping, the jth element of the proximal mapping of L1 norm equals this soft thresholding? Let's see. So assume the function g is L1 norm. Okay, again, Recall the proximal mapping of the norm. What was it? Equation 64. So we need the projection onto the unit ball of its dual norm. What is the dual norm of L1 norm? Recall preliminaries. We already talked about it. The dual norm of L1 norm is L infinite norm, or max norm. We also called it Chebyshev norm. So it's L infinite norm. It's because L infinite norm is the dual norm of L1 norm. Now let's talk about, by visualization, let's see what is the projection onto the unit ball of the L infinite norm. What is unit ball of L infinite norm? It's this. Do you remember? Recall preliminaries. It's this square, including it inside of it, right? So now we are, this is in 2D. In 3D, it becomes a cube, for example, including its interior. Here, we are talking about one dimension already. Therefore, you can see it as only for one dimension. In one dimension, when we are outside of this, projection means that we are here. So when xj is greater than or equal to 1, so then it becomes 1. Its projection is 1, right? When it's less than -1, its projection is -1. When it's in this region between here, so it means we are inside the unit ball. Therefore, it becomes itself. We don't need to, the projection becomes itself. Okay. So now we already talked about it by visualization. Now let's see the jth element of the proximal mapping of L1 norm according to equation 64. So it's xj minus lambda this, and now what is this? Replace it here. So xj minus, when xj is greater than or equal to lambda, this becomes 1. So we will have xj minus lambda. When it's less than minus lambda, this term becomes -1. So we'll have xj plus lambda. In the middle case, well, this becomes xj. So we'll have xj. No, this becomes, sorry, xj over lambda inside of the projection. So xj minus, this becomes xj minus lambda, xj over lambda. The lambdas cancel each other, so it becomes 0, right? This is the soft thresholding function. You hear of soft thresholding a lot when you are dealing with L1 norm in optimization. Okay, this is the proof. Why am I telling you the proofs of these? Because for you to understand what these are, when you understand the proofs, then everything becomes clear to you, what you are working with. Okay, so why are these useful? Let me add a page here to tell you why whatever we talked about, the proximal mapping of the norms, useful. So assume we want to minimize some function f, but especially for example in machine learning, we also see that a lot. You want to have a regularization term, or with some regularization parameter lambda, for example. This lambda, don't confuse lambda with the lambda of proximal mapping. Let me call it gamma, whatever. You say that, let it be L2 norm. You say that I don't want this x to be very large. So I want to minimize the function f, but I want to have some penalty on the size or on the length of the optimization variable. I don't want it to blow up. Probably you can minimize f of x, but x becomes, it's a vector. For example, it becomes 10 to the 6, 10 to the 5, 10 to the 11, something like that. this optimization variable actually might be x star, which minimizes f, but it's not useful when you are coding. In practice, it's not useful. It doesn't make sense to have such a large x. Then you add an regularization term. You say, okay, find an actual optimal value, but I don't want it to blow up. Therefore, you can say this, or so this is penalizing its L2 norm, its length. In another case, you might say, I want to penalize it in another way. I want it to be sparse. So when you want to impose sparsity to your solution, you usually regularize it with L1 norm. Why? There is another visualization for justifying it. Recall the unit spall of L1 norm. It was like this. It was a diamond, right? Assume you wanna optimize the cost function f, but you also want it to be inside the unit spall, for example, inside the unit spall of the L1 norm. So assume you have a two-dimensional function, and this is the unit spall or a scaled unit spall, doesn't matter, of the L1 norm, and you want to minimize f. Of course, the minimization of f is here, but it's very large. It's a huge x1 and x2. You say, no, I want to minimize f subject to being in the unit ball or having a small L1 norm. Then you will see that you will probably touch one of the corners of this diamond. Compare it with the case when you are regularizing it with L2 norm. By the way, this visualization, its credit is for, I think, either Tibshirani or Hasty at Stanford University. He proposed lasso regression. So look it up, lasso regression. Lasso regression has a L1 norm regularization term in regression, in linear regression. So I'm using his justification. I don't remember whether it was Tibshirani or Hasty, one of these two, I guess. I think it was Tibshirani. But see, here you might touch the unit ball when in L2 norm here, which has both L1, which has both x1 and x2. Although its x1 and x2 are small, this is this case. So you are saying that minimize the function f, but here is too large. I want it to be inside the unit ball of L2 norm, or I want this L2 norm to be small. So you see where does this function touch here, and this is the solution with a small x1 and x2. However, here, this is for this case. You're regularizing using L1 norm, and you will probably touch one of the corners. And in this corner, interestingly, x1 is 0, and x2 has a number, but it's also x2 is small. But one of the variables, one of the elements is 0, exactly 0. Here it's not 0. Here x1 is close to 0. Here x1 is exactly 0. Why? Because the probability of the function to touch the corner of the diamond is much higher than the probability of this to the solution to become here when it's a sphere. Although in both cases, x1 and x2 are small. In one of the cases, in L1 norm, x1 becomes exactly 0. Therefore, it's a sparse. That's why for sparsity, you can use L1 norm regularization. But you can use L2 norm for making it a small, but it won't be sparse. But you might be wondering, it seems that, by the way, for this to understand better, increase the dimensionality of a function to, for example, 100. The diamond will have 100 corners. I think you can understand what I'm saying there. Consider a diamond increase the dimension to 3, then it becomes like a 2 pyramids back to back. Then increase the dimensionality to 4, to 5, to 6. You are increasing the corners. Then it becomes, when the dimensionality goes to infinity, you will have a lot of corners next to each other. It becomes like a ball, but with a lot of sharp corners. You can't touch it. Every part has a lot of corners, sharp corners, right? That's why, especially this justification makes more sense when you have a huge dimensionality. Of course, when you touch one of the corners, many of the elements will be 0. Here, one of the elements became 0. But when you increase the dimensionality, many of the elements become 0 at that solution. That's why it's sparse. Is it clear? Now, yes? Is it clear?
Yeah, it's clear.
Great. Okay, now let's consider this case. You might be wondering, it seems that L1 norm is much better than L2 norm, because not only does it decrease the value of elements in the solution, but also it makes it sparse. Why don't we use L1 norm rather than L2 norm always? Can anyone tell me? Can anyone tell me? The reason is this. L2 norm is much easier. L2 norm is a smooth. L2 norm, you can take derivative easily. What is the derivative of a squared L2 norm? Is 2x. What is the derivative of L1 norm? Very hard. I think you need self-thresholding that we just talked about. It's very hard. It's not a smooth. But a squared L2 norm is a smooth. Therefore, many people say, I don't want to suffer for calculation of L1 norm, derivative of L1 norm. Let me use L2 norm. It's good enough. It reduces the values of the the length of my solution. But although it doesn't make it sparse, but it's good enough. It makes my calculations easier. It makes my world easier to deal with. That's the reasoning. So there's a trade-off between whether you want to do it sparse or whether you want to do it easier, in an easier way. That's the difference between them. And by the way, there is a betting on sparsity principle, again proposed by Hasty, Tibshirani, and others in Stanford. What is that principle? It says that when you have an algorithm, an optimization algorithm, assume you regularize it with, if one of them is sparse, using regularization or whatever, you have this exact optimization problem, but its solution is not sparse. So you have two exact problems, similar problems. One of them is a sparse version of the other one. I bet with my blindfolded eyes, I bet that with a high chance, the sparse solution works better. Usually the sparse solution works better, especially in, for example, in many cases, lasso regression works better than ridge regression. So in regression, the L2 norm regularization is called ridge regression. This is lasso regression. Usually, in some cases, not always, but this betting sparsity principle works well in many cases. The sparse solution works better. You can also justify it by Occam's razor in philosophy and logic. In logic, I think you have heard of Occam's razor. Occam's razor says that in philosophy and logic, says that if two things explain the reasoning for one thing, for one phenomenon, which one is simpler? Choose that one. For example, if you are a philosopher, you have two understanding of one phenomenon. You say, okay, this might have happened for reason one, or this might have happened for reason two. Which one should I choose in philosophy, in logic? I choose the one which is simpler, the simpler explanation. An example, this is Occam's razor. An example, I'm hungry. The reason might be because I haven't eaten for several hours. The second reason might be that an alien came and tricked me and magicked me to become hungry right now. But that alien was invisible to me. Which one is the justified answer to why I'm hungry? Of course, what is the simpler solution? Because I haven't eaten for hours. There is no alien that made me hungry. You get my point? This is Occam's razor. Again, here, when you have a sparsity, it's like simplicity. Sparse make it simple. So it's better solution. Okay, now let's go a bit faster to finish the proximal methods, and then we'll have a break. So proximal point algorithm. Recall question 58. Where was that? Yeah, the proximal mapping, the definition of proximal mapping with parameter lambda. Okay, let me come back to where we were. Okay, recall equation 58. I have repeated it here. So this term inside the argmin is strongly convex. Recall preliminaries. Therefore, its proximal point is unique. As it is strongly convex, it has one minimizer. Therefore, this is unique. Okay, you might be wondering, how do we know that the proximal mapping is unique? It might have several solutions. Here is the reasoning. This is a strongly convex, therefore proximal mapping is unique. Also, there is a lemma. I haven't provided the proof here. So the point x star minimizes the function f if and only if x star equals proximal mapping of x star with function lambda f. So assume the function g or f, what doesn't matter. We want to minimize the function f. This is minimized by x star. If x star equals proximal mapping of lambda f x star, it's if and only if. So if this is true, then x star minimizes f also. The other way around. If x star minimizes f, then this is true. Okay, that's another thing. Now, this lemma is used in an algorithm named proximal point algorithm. So proximal point algorithm says that assume I have an unconstrained optimization problem, minimize f of x with respect to x, okay? And assume you can't find its solution as a closed form solution. Otherwise, you would say, okay, take derivative of f of x and set it to 0, and it gives you x star. The same situation that we have in gradient descent. You can't find x star in closed form solution, then therefore we need to do it iteratively in a first order method. And one of the first order methods is proximal point algorithm, also called proximal minimization, proposed in 1976. What does it do? It says that at every iteration, do this. So K denotes the iteration index. So xk plus 1 equals proximal mapping of xk, the previous k in the previous iteration, with the function f and parameter lambda. Okay. So, and according to the definition of the proximal mapping, it's this. We do it until convergence, until xk plus 1 gets very close to xk. And lambda can be seen as a parameter related to the step size. Similar, it's very similar to the gradient descent, as you see. And by the way, recall the Moreau envelope, or Moreau envelope that we defined in equation 59. It's very similar to saying that we are applying gradient descent on the Moreau envelope of the function. So gradient descent is on the function itself. this is kind of saying that let's apply gradient descent on the Moreau envelope of the function. And what is it saying? Let's interpret 67 better. So it's saying that at every iteration, I want to so because this is minimized, right? I want to minimize the function f as desired here. I want to minimize the function f, but I'm doing the change of variable. I also want the solution of this minimization be very close to the previous solution. In other words, I'm having a history similar to the idea of momentum. You can see that when you are studying different algorithms in optimization, you see a lot of connections between them. So you see many ideas come from different algorithms. Oh, in momentum, we had a log of history. It's similar here. Minimize the function f with change of variable to u, but u let it be close to the previous solution, not to have a lot of oscillation, right? Okay. Now we also have composite functions. I'm going to explain another algorithm, first order algorithm, related to proximal mapping. All of these are related to proximal mapping. So assume you want to minimize f of x plus g of x. Sometimes you have minimization of f of x plus g of x, not just f of x. An example is regularized optimization. When you have a function, an actual cost function, and g of x is a regularization term, right? So this is a composite function. Its optimization is called composite optimization problem. You see it a lot in optimization. You see it a lot in different areas such as machine learning. And assume f of x is a smooth function and g of x is a convex function, which is not necessarily a smooth, okay? Then composite problems are widely used in regularization term, okay? Let's see how to deal with them. For solving the optimization, this optimization, let's do this. Let's approximate the function f of u with its second order Taylor approximation, but replace the let's replace the second order gradient with 1 over eta identity matrix. With identity matrix, then you will have this. So in the second order term, replace the second order gradient with this, and you will have this. So the whole thing becomes like this. So you're approximating the function f, okay, around point x. This is Taylor approximation. Then the solution to this optimization problem can be approximated as this. So this is the optimization problem, argmin of f plus g, but we are having a change of variable x to u. Again, why can we do that? Because it's a dummy variable. So you can say argmin of chair f of chair plus g of chair. We don't care about the name of the variable. Okay, it's a dummy variable. So here argmin of u, f of u plus g of u, and then I'm replacing f of u with the Taylor approximation that we talked about. We'll have this. Now okay, this term f of x is a constant with respect to the optimization variable u. Therefore, I can replace it with another constant with respect to u, which is the squared L2 normal of gradient. Okay, I can do that because it's constant. And then consider these three terms using the binomial squared term. What is binomial squared term? Is a plus b squared is a squared plus b squared plus 2ab. So I can write this as this, right? Well, as it is a vector, we have L2 normal squared. Okay. And then I rearrange the inside of the L2 norm to this, and I will have this. Okay. We found this. We proved it in the previous slide. Now let's talk about it. This is exactly the proximal gradient method. So this is another algorithm. named proximal gradient method, also called proximal gradient descent. Don't confuse it with the previous algorithm. Its name was proximal point algorithm or proximal minimization. This one is proximal gradient method or proximal gradient descent. It was proposed in 2013, very close to us. We are getting closer to the state of the art in optimization. Okay. By the way, Boyd, which I introduced to you in this course initially at Stanford University, has worked on proximal algorithms a lot. He has a famous paper on proximal mapping. Okay. Now, proximal gradient method or proximal gradient descent. This is this algorithm, which we proved in the previous slide. It says that the next x in this, so it's iteratively, and in each iteration, we are saying that the set x k plus 1 to argmin of this term. This is exactly this, right? But x is the x in the previous iteration, and we also can have adaptive learning rate. So consider this eta to be learning rate. And okay, let's interpret it now. Let's interpret this or this, doesn't matter, they are the same. Let's interpret it. It says that, what is this? What is this? Or this, doesn't matter, the same. This is gradient descent. This is a step of gradient descent. A step of gradient descent, right? Which we introduced 2 sessions ago. So this is saying that find a u, argument u, which is close to the solution of the gradient descent for function f. So this is gradient descent for function f, because we are minimizing f plus g. So let's find a solution which is close to the solution of gradient descent for function f. At the same time, let u minimize g. This is exactly minimization of a regularized optimization problem, right? So it's saying that find a solution for gradient descent of f, but also try to minimize the regularization term, which is g. This is proximal gradient method. Okay, interesting, very interesting. And by the way, interestingly, why is it called proximal gradient method? Why does it have a proximal term in its name? Because this is exactly equal to, according to the definition of proximal mapping, this is proximal mapping of this. Take a look at the definition of proximal mapping, and you'll see that these two are equal. So it says that find a solution, find one step of gradient descent for f, and then apply the proximal mapping on that with the function g. By the way, I want you to note one thing. Here, in proximal point algorithm, it wasn't for a composite function. The proximal gradient algorithm was for the composite function. There is another difference, interesting difference between them two. Here, when we are saying in equation 67, when we are saying argmin of this, it means that find its minimum, actual minimum. So you are not doing one. Assume for this argmin you can do a gradient descent, but you need to do it, and this is in each iteration. But if you are, you can find the minimum of this term with any optimization algorithm that you want, but you need to find its minimum. You can take derivative, set it to 0. If it's closed form solution, done. But if it's not closed form solution, you need to do it iteratively. Then you can do, for example, a full gradient descent. What do I mean by a full gradient descent? A complete gradient descent until convergence, because it's argmin. So in each iteration of proximal point algorithm, you need to do a complete gradient descent. So it's an optimization inside another optimization. However, in proximal gradient method, you're only doing one step of gradient descent. One step of gradient descent, not the whole gradient descent. So it's simpler. It's simpler in terms of computation. Okay, did you understand what I'm saying? Now, interesting. So far up to this point, whatever we talked about mostly was about unconstrained optimization, first order optimization problem. What if our optimization problem is constrained and we want to do solve it iteratively using first order methods? We can do it in this way. Again, I talked about it briefly a few minutes ago. Assume you want to minimize f of x subject to x belonging to a feasibility set. This is a constraint optimization problem. This feasibility set might have a lot of inequality constraints and equality constraints, right? Then you can convert it to this. We talked about it. You will have a penalty term, but as it is an indicator function, it's a hard penalty term. Therefore, they are exactly equivalent. If you use an actual identity indicator function, if you approximate the indicator function, then this becomes approximate. Okay. Now, what is this? According to we can solve this using proximal gradient method, right? Why? Because equation 71, this is a composite function. This is f, and this can be seen as g. This was the proximal gradient method. Now, the function g is an indicator function now. Let's put it here. So I'm replacing g with the indicator function. And we already talked about it several slides ago. Proximal mapping of the indicator function is a projection onto its set. And what does the whole thing mean? This is called projected gradient method, proposed in 2003, or gradient projection method, or projected gradient descent. These are different names for the same algorithm. Boyd, for example, says, don't call it projected gradient descent because it's not descent anymore. Gradient descent is descent. It's better to call it projected gradient method. Okay, what does it say? Let's interpret that. It says that do a step of gradient descent for minimizing f of x, but after each step of gradient descent, so it's very similar to gradient descent, but at every step of gradient descent, your solution might be infeasible according to the constraint. Project it onto the feasibility set. Project it back to the feasibility set. For example, assume you want to minimize this function f. And this is your feasibility set. You start with assume you start with the feasible points. You do the gradient descent, you become here, for example. Here, oh, you came out of the feasibility set. Project it back to the feasibility set. Do the gradient descent again, another step of gradient descent. You come here. If you are already, after a step of the gradient descent, you are already in the feasibility set, projection becomes itself because you're already in the set. When you are already in the set, projection onto the set is itself. You don't move. But if after a step of gradient descent you come out of the feasibility set, you need to go back to the feasibility set by projection. And why is projection best? Because projection is the closest point in the feasibility set to your solution. So you are saying that how should I say? I deviate from the solution of the gradient descent. It's not good for minimization, but I deviate the smallest amount of deviation because I'm doing projection. Okay, this is projecting gradient method. We have other variants of projecting gradient method, like this. When we have an addition, for example, this was proposed in 2004. we can have an additional variable y, which says that after a step of gradient descent, project it onto the feasibility set, but don't put it to xk plus 1, but put it to yk. Let xk plus 1 be summation of xk and some gamma, which is a parameter, and y minus k. In other words, let is k plus 1 have some impact of this projected gradient projection of the gradient descent. However, let it be close to the previous solution. Another one, and in other words, let it have a log or a history of the previous solution. Again, similar idea to momentum. Another similarity that you might think of is it's very similar to the accelerated gradient method AGM, which Yuri Nesterov proposed. It had also two variables, y and x, where you can see the ideas are repeating in different algorithms. And why do we log the impact of the previous solution? For having less oscillation, like what we had in momentum, right? Okay, we also have projection onto the cone of orthogonal matrices. This is also useful in many cases. I can say that at least in the areas that I know. In machine learning, you see it a lot, especially in spectral methods, spectral dimensionality reduction, spectral clustering. For example, in a spectral dimensionality reduction such as PCA, principal component analysis, in F. Fisher discriminant analysis, also called linear discriminant analysis, in local linear embedding, in maybe isomap and MDS, multidimensional scaling. In many of the well-known algorithms in machine learning, you will see this constraint that I'm going to talk about. Also in telecommunications, I know that they have a lot of this constraint. In physics, theoretical physics, sometimes your optimization problems need the constraint of orthogonality discussed here. So in many areas of science and engineering, you will see this constraint. Okay, this constraint, I mean, x transpose x equals identity matrix. This is the definition of orthogonal matrix. An orthogonal matrix, in an orthogonal matrix, the columns are orthonormal. That's why it becomes identity. So the columns of the matrix are orthonormal. The matrix is called orthogonal, okay? And x transpose x equals identity. So let's see how to solve these problems. Consider the singular value decomposition. If you don't know what it is, I'm talking about it right now. SVD, or singular value decomposition of the matrix, let the matrix X be D1 by D2. It can be rectangular matrix. Okay. So when it's D1 by D2, you can have SVD. So you're decomposing it into the multiplication of three matrices, U, sigma, and V transpose. U is D1 by D1. It's a square matrix. V or V transpose is D2 by D2. Therefore, sigma becomes D1 by D2. Okay. And U and V are orthogonal matrices. Therefore, U transpose U equals I, identity matrix, and V transpose V is also I. And sigma, so U and V, U is called left, the matrix of left singular vectors. V is the matrix of right singular vectors. These are just names. And sigma is a diagonal matrix, as it is a rectangular diagonal matrix, and its values are the singular values. There is a good connection between singular value decomposition and eigenvalue decomposition, but I'm not going to talk about it. It's a bit out of the scope. But you can look at my tutorial on eigenvalue. It's called Eigenvalue and Generalized Eigenvalue Problems. In the appendix of that tutorial, I have talked about the connection between eigenvalue and singular value decompositions. Okay. So let's continue. Consider the SVD of X. Now let's what is X transpose X? So this is X transpose, right? When you are transposing, the order is changed. So V transpose V becomes V and comes here. Then sigma transpose equals sigma because sigma is a diagonal matrix, and you will have U transpose at the end. Okay, so V transpose V we know is I. Why? Because we know that in SVD, U and V are orthogonal matrices. And in the middle, we will have sigma, sigma. So sigma times sigma is sigma squared. So we'll have U sigma squared U transpose. And we want it to be set to I because this is a constraint. This is the constraint. We want this to be satisfied. Okay, now consider this. Multiply U from the right-hand side. So from right, now in matrix multiplication, it's important whether you are multiplying from left or right. Multiply U from right. So you will have these. I times U becomes U, and you will have U transpose U. U transpose U is I because U is an orthogonal matrix. Therefore, you will have U sigma squared equals U. When this equality holds? When sigma equals identity matrix. When sigma squared is I, so sigma is I. Okay. What does it mean? It means that whenever you want X to be an orthogonal matrix, so you have X transpose X equals I, your sigma, the sigma in the SVD of X needs to be identity. When sigma is I, then X is an orthogonal matrix and its columns are orthonormal. In other words, when the singular values of X are 1, because when singular values are 1, sigma becomes identity matrix. It's a diagonal matrix. It becomes identity matrix. Then it becomes orthogonal. By the way, sigma in general case might be rectangular. Therefore, I mean rectangular identity matrix. For example, like this. We might have zeros here. It's a rectangular identity matrix. Okay. And so when your constraint is orthogonality, it means that project it into this state. It means that when you have projection onto the constraint of the orthogonality, means that calculate the SVD of X, calculate U, calculate V, but replace sigma with I and reconstruct X. So X was U sigma V transpose, set sigma to I, reconstruct X by U I V transpose. Then this is projection of X onto the orthogonal cone, orthogonal matrices, the cone of orthogonal matrices. That's very interesting. You might have constraint X transpose X equals lambda I, so scaled orthogonality. In other words, let its I don't want its columns to be orthonormal. I want the columns of X to be orthogonal, not necessarily orthonormal. Okay, therefore X transpose X might be lambda I. Then if you put lambda I in the right hand side here, lambda I, you will see that your singular values must be lambda I, lambda times the identity matrix. So that's the thing. So it's an interesting thing because you have a lot of, in a lot of cases, what does it mean? What I explained was this. What I explained meant this. Assume you are minimizing f of x, some function of x, and this time x is a matrix, such as, for example, let me think, trace of U transpose, X transpose AX, okay? This is a function of X, right? And A is some matrix, some known matrix, subject to X transpose X equals I. How can I solve it? I can say consider it as a composite function. Trace of X transpose AX plus lambda identity matrix. Or don't need, when we are saying identity matrix, I think we don't need lambda anymore. X transpose X, X transpose X. So this means X belongs to orthogonal matrices. So X belongs to orthogonal matrices. Then use projected gradient method for solving that. And in each iteration, do one step of the gradient descent on this, and then take the solution of the one step of gradient descent, apply SVD on it, set the singular values of that to identity to 1, and then reconstruct the solution. Then go to the next iteration, again, do one step of gradient descent, then project it again. Do one step of gradient descent, then project it again. Now I think you know how to solve it, right? Any question? No?
No.
Okay, great. So we can also have projection onto convex sets. So assume we want to project a point onto the intersection of C closed convex sets. Assume we have some sets and they should be convex. Assume you have some sets I have some points. I can use this, the optimization algorithms that we talked about, projected gradient method and these things, in order to solve this problem, which is not an optimization problem. It seems not to be an optimization problem. What is the projection of this point? I don't want to minimize any function. I just want to find the projection of these onto the intersection of these sets. So which is here. This is the intersection of the point. What is the projection of this X onto the intersection? I think the solution will be here, something like this, right? But I want to find it. And these sets might be multidimensional, and the point might be multidimensional, so it might be hard. You might have a lot of sets. Okay, let's see. So this is the intersection of the convex sets. Let the number of sets be C. I can convert it to an optimization problem by saying that this is a good technique in optimization. Minimize some fake function. You can say X or some function, fake function such as 1. Minimize 1. Can you believe that? Minimize the constant function 1. You can do that. Or you can say minimize X. But there is a difference between these two. I will tell you what is the difference. But minimize some fake function, but let the constraint be what we want. X belongs to S1 and S2 until SC. So we know that if we solve this optimization problem, X must be feasible, right? Because we are satisfying the constraints. It means that X must be in the feasibility set. Therefore, so although we are optimizing some fake function. Interesting. Now we can say it's if you do projected gradient method, as it's a fake function, we don't have the step of gradient descent anymore, and at each iteration we are just projecting onto the constraint. And what is the projection onto the constraint? Saying that we are doing it iteratively. We can do it in different ways. Either do it first, project onto one of the sets, then project the solution of that projection onto the second set, then the third set. So we have some order. Here we have some order. The order matters. In order not to have dependence on the order, we can say that at each iteration, project onto each of the sets then take the average of the projection. Of course, when you take the average of the projection, it might not be in the intersection anymore, right? But gradually you converge to the intersection of the sets. And this is called projection onto convex sets. What is the difference between these two? When you set the fake function to some function which is not related to x or to x. When you are saying that minimize 1, then you're saying you're saying that you want to actually find x which satisfies the constraint and nothing else. But when you are saying that minimize x subject to this, means that find the smallest x which is inside these constraints. Assume in this visualization that I had, assume this is the origin. Okay, so here you might not find this because the length of this vector is larger than the length of this vector. So when you are saying that minimize x subject to this, says that find the smallest x which is inside this intersection. But when you are saying that minimize a completely fake function such as 1, then you don't care about the length of x anymore. You find an x which is in the intersection. So this is an interesting thing because it's not an optimization problem, but you are using the optimization algorithms in order to find the projection problem, which is not an optimization problem. Any question? No? Okay. Some slides of this slide deck were inspired by the lectures of Professor Kimon Fantolakis at the University of Waterloo, Department of Computer Science, especially the algorithms in the first order methods such as gradient descent and accelerated gradient descent and stochastic gradient descent and those things. Some of them were inspired by Professor Stephen Boyd, especially the algorithms in the Proximal methods. By the way, I forgot to mention the slides for the portion about the backpropagation are inspired by the lectures of Professor Ali Qudsi at the University of Waterloo, Department of Computer Science and Statistics. Also, I will put all of these links in the description of the YouTube video. Also, you can see the backpropagation things and many of these algorithms, their explanation in our tutorial. Our tutorial in reference 38. Let's review the references very fast. So you can look them up, but I think it's the ones that I remember. This was the Cauchy, because do you remember gradient descent was initially proposed by Cauchy. This is not the dates that this is a paper which explained that Cauchy talked about gradient descent. Also in Hadamard, so Cauchy and Hadamard jointly, we can say in different times, I guess, they proposed gradient method and gradient descent, and they improved that. So Hadamard did this in 1908, so it's very old. So steepest descent, you can take a look at it by Curry in 1944. Armio's paper, do you remember Armio line search or backtracking line search, proposed in 1966. Armio was a great scientist in optimization. You can many of these algorithms, first order algorithms are, and also some of the second order algorithms, especially in quasi-Newton methods. These are explained in a famous book in optimization by Nocedal and Wright, Numerical Optimization. The Wolfe condition, which I said we'll see more in the second order optimization, can be seen in this paper in 1969. SUMT is very famous for its theoretical papers, especially in optimization. So SUMT is a very good journal. And this is the paper for backpropagation, original paper, 1986 by Rumelhart, Hinton, and Williams. It was published in Nature. Also, I don't remember this reference. What was it for? And this is the book of Boyd, published in Cambridge University Press. This is the, I think this is the AGM, accelerated gradient method, the paper for that in 1983 by Yuri Nesterov. I guess this is a Russian paper. Many of the initial papers or famous papers of Nesterov are actually published in Russian, and they were translated to English. This also Yuri Nesterov, this is the book of Yuri Nesterov, which I initially introduced to you at the start of the course, focusing mostly on the first order methods. This Yuri Nesterov, one of these is for accelerated gradient methods, and some of them might be for the variants. This might be a variant of AGM or these things. I don't remember exactly which one was for AGM. I think this one was for AGM, 1983. Yuri Nesterov also has a smooth minimization of non-smooth functions. You can see what this reference was for in the slide deck. Also, as you see, many of first order methods are proposed by Nesterov. Gradient methods for minimizing composite functions. Composite functions we just discussed in this session. And what was this for? I don't remember, but you can see these are very important optimization and mathematics journals, such as Annals of Mathematical Statistics, a very important journal. And this is for stochastic optimization, 1998, by Buto et al. And what was this for? Okay, this is the famous book on deep learning, because backpropagation is related to deep learning by Goodfellow, Benju, and Corville in MIT Press. This is my tutorial on sampling algorithms from service sampling to Monte Carlo methods. Do you remember I talked about the variance of the stochastic gradient descent optimization? I referenced this. I said you can look it up, the proof there. This one, stochastic gradient descent method. Okay, these are about for stochastic gradient descent algorithms. This is for accelerating stochastic gradient descent, and also SAG. I think this might be for SAG. It was published in NeurIPS, a very important conference in machine learning. And many of the optimization papers are published in machine learning conferences and journals, such as NeurIPS. This is adaptive subgradient methods. So subgradient is for gradient for the non-smooth functions. We might, if we have time, we'll go over them. And this is the. Do you remember when I said I think prompt, which algorithm, which was, or Adagrad or prompt, which was used for developing Adam. I said it was proposed by Hinton et al., Hinton and Tillman, and yes. So this is RMS prop paper. This is R prop paper. RMS prop was based on R prop paper. This was the paper. This is the slide deck for the that famous algorithm, I think, RMS prop, which inspired the Adam algorithm, and it wasn't published. So it was just a slide deck at the Department of Computer Sciences in University of Toronto, but it was a very famous, important slide deck by Hinton et al. And this is the paper of Adam, very important paper. this is the recent paper of Boyd. I said Boyd is working on proximal algorithms, so published in 2014. Boyd publishes a lot of tutorial papers and important papers, lengthy papers about optimization, especially in the Journal of Foundations and Trends in Optimization. You can look them up. Moreau decomposition, Moreau envelope, old, proposed in 1965. You can see this is the paper, and I think it's either it's French or German. I think it's French, and because at that time, centuries ago, a century ago, English was not the main language of science. Nowadays it is, but especially, for example, in optimization, Russian was a very important language, and also in physics, German was like at the time of Einstein and Planck, Max Planck, and they were proposing their papers in their own languages. So functional analysis, you can look it up. It's by Yosida, and it's a book in 1965. This is Moreau, a paper on Moreau-Yosida regularization, published in 1997. Again, Moreau was a famous and important scientist in optimization and mathematics. You can see this is also not in English. And also some tutorial on first order methods in optimization by Beck. Yeah, I think this is the last slide in this slide deck. So what is this one? Okay, I don't remember the 32. The 33 is about the overfitting and regularization. We talked about regularization a lot. You can see it in my tutorial about regularization in this paper. We also have shrinkage thresholding for inverse problems. I don't remember which one was this for. I hope I had cited, I forgot to cite the paper of lasso regression by Tipshurani, but you can look it up. That's also an important paper. We also have papers on convergence properties of the gradient method. This paper, this is the paper of projected gradient method proposed in 2004. Also projected gradient method here proposed in 2003. So these are the papers for projected gradient method. This is also for projection. We talked about projection on all of these in 1996. And finally, this is the paper tutorial paper for my tutorial paper for optimization. So, okay, let's have a break. If you don't have any question, is there any question? No? Okay, first order methods are done. Now let's have a break, and after break, we'll start the second order optimization. Let's come back at 9:15, okay?
Hi, man. Actually, I had a question regarding the assignment.
Yes, sure.
So actually, I want to know, like, so in our question, we have to find.
I have a question. What's the maximum speed of portion at 11 turbo?
So, sorry, I heard two voices. What was it again?
Does Eric want to speak first?
Okay, that's fine. What was your question again?
So yes, so like in the question, we have to find two iterations of the gradient descent. And
yes.
We need to find out the optimal point of the x star. So we need to consider the x star as the x2, or do we need to derive the function and then get the x star?
X star, you mean?
Yeah, the optimal point that we need to get.
After two iterations, I mean, yes.
So we consider the x2 as the x star?
Yeah, of course, it's not x star, but I'm saying that assume, do you remember the convergence criteria that we talked about? Let the maximum number of iterations be 2. Although it's not yet converged completely, but let it be there. So start with x0, then find x1, then find x2. x0 I already gave you, let it be 1.
Yes, it's 1. Okay.
Yes.
Okay, so we can just consider it as x stars because it's 2.
Yeah, because I didn't want you to solve the whole gradient descent.
Yeah, that was my confusion. Okay, thank you.
Okay, thanks. Any other question? No? Okay. Hi. So let's resume the session. By the way, before we start the second order methods, I think you know the reasoning for the name proximal in proximal algorithms, right? I think you already know that, because in definition of proximal mapping, we said let's minimize argmin of G plus 1/2 or 1/2 lambda U minus X L2 norm of S squared L2 norm of U minus X. So we want to minimize G with respect to U, but we want U to be close to or proximal to X. But because of closeness or proximality of U to X, we call this proximal mapping. And the algorithms which use that proximal mapping are usually called proximal algorithms. That was the reasoning behind the name. Okay, let's continue. Let me share screen. Okay, so so far we talked about so initially we started with preliminaries and then first order methods, and then linear programming, and then integer linear programming, sensitivity analysis, and then we went to first order methods, and now we are going to talk about second order optimization. So first order optimization uses gradient or derivative, first order derivative, and second order optimization makes use of both first and second order derivatives. So it uses gradient and as well as Hessian. Now let's talk about them. So first talk about Newton's method. Let's talk about Newton's. For talking about Newton's method, we need to first talk about Newton-Raphson root finding method. Do you remember when I think you already have learned that, you might have learned that Newton-Raphson method in your numerical method course, numerical analysis. So when you have a function, which might be a complicated function, you set it to 0, you want to find its roots. Like you have a function, you set it to 0, you want to find its roots. But if you can find, by setting it to 0, you can get X as a closed form solution. So you can find X in the left-hand side alone, and right-hand side is not dependent on X, then it's done. You find the roots. However, the function might be complicated. For example, hyperbolic tangent of X over 1 over plus sine of X. I don't know, very complicated thing. X squared plus 3x equals 0. How can you find it in a closed form solution? Therefore, you have to do it iteratively. And one of the ways to find the root of a function is Newton-Raphson. So proposed by Newton and Raphson together, jointly. So it is this. It says that iteratively, you start with a point, and then you say xk plus 1 equals xk minus f of xk over derivative of f of xk. So f evaluated at xk and derivative of f evaluated at xk in the denominator. And this is Newton-Raphson algorithm. You can see its connection. It's very similar to what we have in iterative optimization. Okay, let's see how we can use that. So we had this is Newton-Raphson method. And okay, now forget about Newton-Raphson. Assume you have an unconstrained optimization, minimize f of x subject to with respect to x. It's an unconstrained optimization. In order to find its minimum or maximum or its extremum, what do? What we learned in high school. Take derivative, set it to 0. All right. We take derivative, set it to 0. It's also this simple idea of take derivative, set it to 0 for finding the extremum of the function is also called first order optimality condition. Okay. Therefore, we need to find the root of gradient of f equals 0. So Newton-Raphson said that in order to find the root of any function, you can use Newton-Raphson. Now the function here is a gradient of function f. So you can see gradient of f as another function named g. So g equals 0. What do we do for that in Newton-Raphson? In Newton-Raphson says xk plus 1 equals xk minus g of xk over gradient of g of xk. Now replace g with gradient of f. Then you will get this. So g is gradient of f. Gradient of g is gradient of f. So it's second derivative of f. So it's derivative of f. Therefore, we'll have this. And this is Newton's method. This is Newton's method for solving this optimization problem, this unconstrained optimization problem. Okay, but this is for so by the way, we have added this here. We didn't have this. This is just for a learning rate. If you set the learning rate to be 1, then it will be very similar to the Newton-Raphson method. Learning rate is greater than 0. Okay. And this is second derivative. This is first derivative. As you see, it has second derivative, so it's a second order optimization. And it's Newton's method because it's very similar to the Newton-Raphson algorithm. Okay. Newton worked on that. So if now here, when x is a scalar, we can have the second order derivative of f of xk in the denominator. When it's not a scalar, and when x is a vector, therefore gradient of f will be a vector. Therefore, Hessian of f will be a matrix, as we discussed about it in the preliminaries. Then we can't write the matrix in the denominator. We should write it as the inverse of matrix. So because in a scalar form, you can write it in this way, right? You can write this. Even if it's a scalar, you can write the denominator as this. Right? Now, when it's a matrix, it will be inverse of matrix. So this is the Newton's method for optimization when x is a vector. Then gradient will be a vector. This is a vector. This is a vector. Gradient is a vector because f is a scalar. So gradient of a scalar with respect to a vector is a vector. Recall preliminaries. This is a Hessian matrix, inverse of Hessian. This is inverse of Hessian, right? Okay. And now, briefly talk about Newton's method for unconstrained optimization. We already proved that, derived that, but now let's a little justify it, analyze it. So minimize f of x with respect to x. Assume f is a convex function. It can. So by the way, these gradient descent and Newton's method, all of these start with assuming that the function is convex. But when the function is also not convex, they work well in practice. Although they might not find the global minimum or global optimization variable, but usually the local that they find is good enough for our practical cases. Okay, for example, in machine learning neural network optimization, cost function is highly non-convex, but usually it finds a good solution. Okay, so don't worry about whether it's don't be worried about this. But iterative optimization can be first order and or second order. So this is the general case for updating in the iterative optimization, right? Xk plus 1 equals xk plus delta x. This update continues until delta x becomes very small and we converge. In first order optimization, in gradient descent, we already saw that it's minus gradient of f, this delta x, or minus eta gradient of f, minus some learning rate times gradient. However, here we'll see that it's different. The delta x in which we saw that in previous slides, that the updates in the Newton's method is minus inverse of Hessian times gradient. Let's justify it and analyze it. So it's justified in this way. F of x, we can write its second order Taylor approximation as f of around the optimal point. Assume as it is a convex function, we assume that we know that there is some x star, and around that, let's say f of x star plus gradient of f of x star, x minus x star, and this term. So this is second order Taylor approximation. But we know that at according to the first order optimality condition, we know that at the optimal solution, the gradient is 0, right? Because we know that it's in either in maximum and in minimum gradient are 0. Gradient is 0. Therefore, this term goes away. So we'll have only these two terms. And as you see, the function is approximately almost quadratic. This is a quadratic, right? This is quadratic near the optimal point. Near the optimal point, as this term becomes 0, we're almost quadratic. So Newton's method is saying that inspired by the fact that near optimal solution, we are quadratic. So our update can also be a quadratic, can use a Hessian in it. So this is a justification of Newton, because we want to find the x star finally. So what we know at around that, this is quadratic. Okay, we can also sometimes in the literature, they write this equation 7, they rearrange it and write it in as equation 8. So from the left, they multiply the sides by gradient Hessian of f, Hessian of function. So we'll have Hessian delta x equals Hessian times Hessian inverse becomes identity. So minus gradient of f. Okay. And okay, Newton's method for equality constraint optimization. Now, so far, I think you might have heard of this. It was easy, Newton's method for R constraint optimization. But what if we have constraints now? So here it is. So assume that we want to minimize some function f subject to ax equals b. So this encapsulates all of the equality constraints, because the A is a matrix. So it we can write the equality constraints as this, right? Each line is a equality constraint. So this is currently I'm assuming the constraints are all equality constraints. We'll add inequality constraints later. Okay, after a step of updates, so let the step of update be delta x, also denoted by p. So I denoted by p here. The optimization is after one step, the optimization becomes this, because x becomes x plus p. Now this is the updated x. So I put x plus p in the f and also in the constraint. Now let's write the Lagrangian of this. The Lagrangian of this is the f of x plus p plus nu transpose. Nu is the dual variable for the equality constraints, and as we have multiple equality constraints, we might have, so it's a vector, right? So nu transpose and this is the Lagrangian. Okay, now let's consider the second order Taylor approximation of f of x plus p. What is this? It's this f of x plus gradient of f transpose p plus this, the third term. Okay, now let's substitute this Lagrange, this second order Taylor approximation inside the Lagrangian. We'll have this. Lagrangian is, so rather than this, I'm putting its approximation. I will get this. I'm repeating it here. Okay. According to KKT conditions, the primal and dual residuals must be 0. So we do remember KKT conditions. We said that the derivative of Lagrangian with respect to x should be 0. Also, derivative of Lagrangian with respect to the dual variables should be 0. So derivative of x with respect to x, what is it? So it's the first term is this. It becomes gradient of f with respect to x. This is gradient, so its derivative becomes second order derivative of f of x transpose p. This is second order derivative, so becomes third order derivative. This is nu transpose ax. Other terms are constant with respect to x. So nu transpose ax, derivative of that with respect to x becomes a transpose nu. Okay. And set it to 0. Now, usually when you take derivative, it becomes smaller and smaller, the function. For example, maybe x3. Take derivative, it becomes 3x2. Then take derivative, it becomes 6x. Then take derivative, it becomes 6. Then take derivative, it becomes 0. You can see it's becoming smaller and smaller. So you can ignore the third order derivative compared to the second order and first order derivatives here in this term, approximately 0. So ignore that. If you ignore that, you will have this, rearrange this equation, you will get this. Okay. And also take derivative of Lagrangian with respect to the dual variable. You will get this, because this is a linear function with respect to nu. You will get this. By the way, we know that according to the original optimization problem in equation 9, it should be, because we know the solution should satisfy the constraint to be feasible, right? We know that ax must be b. Now, therefore, if we consider ax equals b, so ax equals b is cancelled by this minus b, so we'll have only ap, and this needs to be 0 because of KKT condition. So we have these two, so we have this and these two. Therefore, we have a system of equations. We can write it in this way. We can say in matrix format. So this is saying the second order derivative transpose p plus a transpose nu equals minus gradient of f. The second line, it says a, so this a is a matrix. So this is a block matrix. So this is a block matrix, a block matrix, block matrix, block matrix. You can understand what I'm saying. This is also a vector. This is a vector. So this is the concatenation of these two vectors. So this is a times p plus 0 times nu. There is no nu here, equals 0. Right? Okay, now I have it. So let's solve this system of equations. We can solve that. There are some methods in order to make it faster. There are some ways to solve the system of equations in computer faster using Cholesky decomposition and several decompositions that we have in matrices. You can look them up. But there is one session of Boyd on optimization in Stanford, which talks about these ways to make it faster in optimization 1 of Boyd. Okay, so we can solve that. So we don't need to worry if it becomes a huge system of equations, because we can use Cholesky decompositions, all of those things to make it fast, to solve it fast. Then this gives us p and nu, because these are the variables, right, of this system of equations. And what is p? P is delta x. This is exactly what we want in Newton's method, the update delta x. And nu is the dual variable for this delta x in this iteration. So in each iteration, we are solving a system of equations. So when we have equality constraints in Newton's optimization, in each iteration, we need to solve equation 14 as the system of equations. And it gives us p, which is delta x, and its corresponding dual variable nu. Okay, that's it. So first up, we assumed that in the previous slide that we start from a feasible point. So assume our initial point is a feasible point. Newton's method says, I don't care even if you start with a non-feasible point, even if you start with a point which doesn't satisfy the equality constraints, that's fine. I can solve it. How? In this way. Newton's methods so can start with a non-feasible point. We need to tweak the first iteration only a bit in order to handle non-feasible point. So if the initial point for optimization is not a feasible point, it means that ax minus b is not 0, which is equation 13. No, that's equation 13. This was, do you remember, this was the ax equals b was the constraint. Was the constraint here. We use this constraint here. Now, when in the first iteration, if we start with a non-feasible point, we can't use it here anymore because it's not satisfying ax equals b. Let's see what we should do. Then derivative of Lagrangian with respect to nu becomes ax this. Then we can't say ax equals b to cancel b. Then we'll have this. So rearrange it, we'll have this. Again, that's fine. So we had this, equation 12. Now we have equation 15 rather than equation 13. Let's put them together as a system of equations. There is a difference in the second line of this system of equations compared to equation 14. Equation 14 assumed that the point is feasible, right? So this is the only difference. But in the second and third and so on iterations, we don't need to use equation 16 anymore. We can use equation 14. Why? Because we know the updated solution will be feasible. Will definitely be feasible. So as long as the solution is not feasible, we can check. Maybe. Just for the validity check, after the first update, you can check. Most often it is feasible. If it's not feasible, you can use equation 16. As long as you hit a feasible point, so assume that you start, maybe after one iteration, in rare case, you might not get feasible. You go until you get feasible. Whenever you get feasible, you will be definitely feasible until the convergence if your function is convex. If it's not, it might not be convex. Then in that case, you can always check whether it's feasible or not. If not, you can use equation 16. So in summary, Newton's method says that I can handle non-feasible point too. And I can use equations 14 or 16 for update in every solution. That's interesting. Any question? No? Okay. Interior point and barrier methods. So what if we have inequality constraints now? Let me briefly mention until whatever we can get, and then we'll continue in the next session. So now assume the general case optimization problem, where we have minimization of f of x subject to yix less than or equal to 0 for M1 inequality constraints. We also have several equality constraints. So we have both equality and inequality constraints. This is a general case. Then we should use some methods called barrier methods, and we'll see why they are called barrier, or also called interior point methods. There are many papers on them. They're very interesting. Many optimization toolboxes use barrier methods or interior point methods. So this, I can say these are the default optimization methods in nowadays optimization toolboxes. Because no matter whether your optimization problem is a linear problem, you can even use linear. You can even solve linear programming problem by interior point methods, right? Because it is solving a general case scenario. But usually when it's a linear programming problem, you don't need to go and use interior point method. You have a simpler solution, and that's a simplex method, right? Okay. So interior point methods were first proposed in 1967. And they are also called Unconstrained Minimization Technique, UMT, or Sequential UMT, SUMT. But why? Because they convert the problem to unconstrained problem and then solve it iteratively. That's why they're also called unconstrained minimization technique or sequential unconstrained minimization technique. The idea is this. Again, we are going to use indicator function. We are using indicator function for converting constraint problems to unconstrained problems a lot in optimization. This is a good technique. So when you have this problem, optimization problem, you can convert it to this. Let's not touch the equality constraints because we know how to handle equality constraints in Newton's method. We already talked about it several minutes ago. So our only problem here are the inequality constraints. Let's put them as a regularization term with indicator function. And as it is indicator function, these two are exactly equal because this is a hard penalty. However, we'll see if we have to approximate the indicator function, then it becomes an approximation. Because of coding, we might need to approximate it. Okay. So we are saying that if this for all of them, this is satisfied, then this becomes 0. If at least for one of the inequality constraints, this is not satisfied, the whole thing blows up. Because if you have one term in the summation, one term becomes infinity, we don't care anymore. The whole thing blows up, right? So we know that the indicator function is not differentiable. Therefore, it's not a smooth. The indicator function, let's draw it. It's this. It says, assume this is yix, this is the constraint. For example, yix is, what should I say? X minus 3. And this is 3. Okay. X minus 3 less than or equal to 0. It means that x should be less than or equal to 0. So for indicator function for yix equals x minus 3, assume x is a scalar in this case, it will be this. It's a completely non-smooth function. Then we need to approximate it, and we'll talk about it in the next session. We don't have enough time to go over it. So just a brief heads up is that we are gonna approximate this sharp function with a soft function like this, which is a logarithm function. That's why we call it log barrier or logarithmic barrier. But we'll talk about it in the next session. And this is called interior point method. Any question before we conclude the session? Oh, by the way, do we have 5 more minutes? Let me go over. Let me talk about it. I think it's interesting. Let me talk about it. So we can approximate this indicator function by differentiable functions. Many differentiable functions we can use, and these are called barrier functions. One of them is logarithmic barrier. So we can use different functions which can approximate this. Not only logarithm can work. Many different smooth functions can work. One of them is logarithmic barrier or log barrier in short. So it's this. It approximates this constraint to be -1 over t logarithm of minus yi of x with the parameter t. This is a parameter, and t is greater than 0. Usually it's a large number, such as 10 to the 6. And it approximates this hard indicator function by a smooth function. Here you can see this is yix. So yix should be less than 0, right? So for less than 0, we want it to be 0. But when it gets larger than 0, it should blow up. So a smooth function is this. This is log. And when we increase t, we have better approximation. But increasing t also blows up this, because Yeah, 1 over infinity becomes 0. So this term becomes closer and closer to 0. So to approximate this 0 better. And this term also becomes close to this. It becomes infinity. So close to this will have infinity times 0, which is not determined. But I'm saying that t should be large. The larger t, the better approximation we have. So we can replace, so we can convert this problem to this. So we can replace the indicator function with the approximation with the log barrier, and we'll have this. We'll have this. And by the way, what is this? This is a constraint optimization problem with only equality constraints. Then how can we solve it? We solve it in the same way that we solved the Newton's method with equality constraints. We talked about it here in this section. Here, we talked about it, right? Therefore, we converted it to a problem which we know how to solve it using system of equations. Maybe we use Cholesky decomposition, all of those techniques to make it faster. That's it. So we can solve the general case optimization problem, which was this. This we solved it, we converted that. And this is called the interior point method. And if the problem is convex, then the solution they should converge to x star, and nu's also should converge to nu star, because we only have nu here. We don't have lambda anymore, because we brought the inequality constants as a penalty in the objective function. So we have nu for equality constraints, and the f values should decrease, and the dual function values should increase. And this is also, this interior point method or barrier methods are used a lot in many optimization toolboxes, such as CVX. CVX is a very famous optimization toolbox in MATLAB. Also, they have its Python version. Accuracy of the log barrier method. This is the last slide in this session. So assume that the optimum problems for optimum for the problems 17 and 22. What was 17? 17 was this. Was the original optimization problem, I believe. Yes, this is the original optimization problem, which was the general case optimization problem. And 22 was its approximation using the log barrier method. This was 22. So we are saying that let's compare their solutions. If the optimal of the original is f star, and the interior point method log barrier is f star r, then we'll have this. F star r is sandwiched between f star and f star minus m1 over t. I haven't proved it here. You can see that our tutorial for the proof. It is in the appendix of that tutorial. But let's interpret that. What does it mean? When you increase t, this becomes 0 almost. So when fr star is sandwiched between f star and f star, it means that fr star equals f star. But when t is smaller, it means that the approximation of the log barrier method, log barrier, is not good enough. Therefore, you will be sandwiched between f star minus m1 over t, some value, and f star. So it might not find the f star exactly. However, interestingly, fr star, we know that is less than or equal to f star. So the function value, the optimal function value of the converted problem using the log barrier method is less than the minimum of the original optimization problem. However, when t goes to infinity, this becomes exactly equal. So the accuracy is good enough. That's why interior point method works, log barrier method works. That's it. We will continue the second order optimization in the next session using, we will continue with the quasi-Newton's method and some other topics which I need to think of the order, in which order I should tell you. Any question before we conclude this session?
No.
No? Okay. I hope you enjoyed this session. I think we learned a lot. Do you agree? We learned a lot with
Yes.
Yeah, it was good.
Yeah, great. Okay, thanks. Okay, have a good night. See you next week.
Okay,
Thank you, Ben.
thank
Have a good
thank
night.
you.
Thank you.
Good
Thank
night.
you.
Bye.
Thank you. Good night.
Hello.
Hi. Professor.